just all about what? Inductance and what? Induction. Now the former definition was what? Self-inductance. Now let's go to transformer. We are going to read through. The transmission is very easy and straightforward. The static machine used for transforming power from one circuit to another without changing the frequency. This is a very basic definition of transformer. Now, since there is no rotating or moving parts, so transformer is a static device. You can see, you go to at every junction of your homes, or of the street, you definitely see some devices there that are static. They are all what? Transformers. You can see, what are they used for? They are used for transforming. Are you seeing it? They are used for transforming power from one circuit to another. Under that, we see the types of transformers. We have what we call step up or step down transformers. We have what we call the three-phase transformer or single phase. We have what we call two-winding transformer or your auto transformer. Then we also have what we call the outdoor transformer or the indoor transformers. They are all types of transformers. The two-winding transformer and the auto transformer is generally used when, as those type of transformer is generally used when ratio between the high voltage and the low voltage is greater than what? 2. Now it is cost effective and to use data where the ratio between the high voltage and the low voltage are less than 2. Now let's look at that step up and step down. That's what is common around us here. Look at, there's what we call the normal grid. You know, some of you that must have seen all these, a very big mast, you understand. Now the cable is a very thick cable that passes through. Now this particular cable passes through interstate, you understand, right from the national grid, where that is from your Kanji dam and so the power that is actually bringing this particular train cuts interstate. Now what it does is that for every state there is a particular distribution junction, you understand. We have another meaning. It's not really massive transformer that collects from the national grid. Now when it gets to that particular distribution point, you now step it down, you understand, to what is now being consumable. Now it is from there we now have the local transformers. Now the local transformer, the one found in your street, this one will now actually collect it. Now it is from here you now have your street poles where it will now take the voltage into various forms of consumption. But whoever that wants to blow his or her house up, if he tries to connect to you can't even get there. So that is just the mechanism that is being used here. Now I'm going to come back to actually give you some kind of breakdown as regards the calculations. You can see the questions there. For instance, look at the number 1, talked about a transformer having the total number of windings and the voltage involved. Here is just the formula you use, your E1 over E2. Now we said our E1 with respect to the total number of winding is the phi over dt. Now your phi here is with respect to what? Flux. Now if we proceed, you have your what? E1 over E2, which equals the total number of winding, N1 over N2. You understand? So this is the formula that will actually be used. Your E here stands for your EMF, while your what? N stands for your number of what? Winding. I'll be looking at a simple alternate current. There is what we call direct current, and there is what we call alternate current. Now, a direct current is always being generated by our normal PHCN. You understand? What you have been given is direct current. Why? Because the devices that are actually being used are already being stabilized. You understand? They are high voltage that are being broken down. That is being broken down manually. But your alternating current here, you understand, is directly from probably your generator. Now these generators, whatever they bring, you consume. Now most times that's why it's not really advisable for you to go for a very smaller generator that will be having fluctuating power. Now if you have a fluctuating power, it can blow up some of your devices. But for your PHCN, they give you a direct current. Why? Because what they do is that they have they generate a very high megawatts of power. So it is the megawatt that is actually being broken down for total consumption. For adequate distribution. You understand? For people's consumption. So if maybe that breaking down is taking place, what will now actually be produced is a direct current. So that's just the major differences between your DC and your AC. DC means direct current, while your AC means alternate current. Now let's do the last, the next topic. We talked about simple alternating current. Now we're looking at alternating current as a whole now, simple alternating current. Now under our introduction, we have during some of the history, some histories that was actually written there. George Westinghouse invented the alternating current, which with sinusoidally, you understand, that's the sine wave. This is what they call a sine wave. You have a wave. So we are going to be using a graph here to be analyzing our results. It's called a sine wave. There's also another one here. Goes through here, goes through here, goes through here. You understand? So when you get to your institution, you'll be able to see. Employ the use of the transformer can be used to what? Step down or up. Now your AC, which DC cannot. You understand? Now it can step down your what? Transformer. It can also step up your transformer. Now what actually happened is that immediately you step down or you step up, you definitely obtain a DC current. You understand? Now if you look at that statement, which DC cannot. Now a low voltage transformer are safer for consumption. You understand? Now which are safer for consumer use, but high voltage with low current are best for long distance power transmission. You understand? Now the high tension analysis that I was giving the other time. Now the high tension has a very high voltage. That's why it can move a long distance. Because the farther the distance it goes, then the more sustainable the current that is actually on it goes. You understand? So from there, you'll be able to deduce that it can travel as far as, let's say, far north. If I say far north, let's say Maiduguri. For Maiduguri down to Lagos. On the same wire, you understand? With almost constant volts. All these things, when it comes to movement of what? Charge, they are all subjected to what? Resistance. A lot of things could make them what? Have resistance on the wire. It could be by breeze, it could be by sunlight, it could be by rainfall. But when you have a high tension, high voltage, nothing restricts it, because on single wire we have thousands of what? Voltage. We have nature of what? Alternating current and what? Voltages. Now, alternating current or voltage is defined as one which will vary with time about a mean value. That is, when you talk about, if you are looking at, okay, let's say for instance now, there's what we call mean value. This mean value is what we call your peak value. That's your I naught. Now, there's also what we call root mean square value. So for your current now in simple alternating current, your current can either be I naught or IRMS. That's your root mean square. You understand? So I'll be looking at the difference between root mean square. So mathematically, your root mean square of current is the same thing as equal to your I over what? I naught over what? Root 2. So this is one good formula that will be used to, if you are to convert your what? Root mean square value, you understand, to what? Peak current, or that's I naught, that's your peak current. If you want to convert it to your root mean square value, you just apply this formula. If you are given peak current, convert it by dividing it by, by dividing root 2 by it to obtain your root mean square current. So those are the values we will also be looking at. Now let's proceed. Now under our sinusoidal instantaneous current. Okay, now mind you, this is your what? Current, and this is your voltage in terms of graph. Now if you are to draw the write out the sinusoidal formula, you have your I, which is equal to your I naught sine omega t. I naught sine omega t. If you are looking at for your voltage, your voltage will be V naught sine omega t. So these are the two formulas that we will actually be making good use of, as we proceed in this series. Now let's go to peak and root mean square value of alternating current. It is defined as the value of the steady current which will dissipate heat at the what? At the same rate in a what? In a given resistance. The alternating current is defined as the value of the simple current which will dissipate heat at the same rate in a given resistance. So remember, I said your I RMS is same thing as I naught over what? I root 2. Your V RMS is same thing as I naught over what? I root 2. over root 2. So from there now, alternating current in resistors, inductors and capacitors. So we'll be looking at number one parameter that is being used. We have your resistor, we have the inductor, and we have the what? Capacitor. Now, if these three parameters are actually being considered, now there are times that you need to what? Relate two of them, as in one by one, as in one against each other. You can relate your resistance and inductor, you can relate your inductor and capacitor, you can relate your resistor and capacitor. If you are looking at only resistor, now you must be able to draw your diagram for only your resistor. Now this is your AC source. That's the diagrammatical notation for AC source. Now if you are linking your AC source, you are now linking it to what? A resistor. Are you seeing it? So you should be able to draw a diagram. Now if you are doing this now, this is the AC source, this is the resistor that is being attached. Now what will our graph look like? Your graph will look like this. Are you seeing it? Now your voltage will go upward. You understand? Now to come this way. Now another one goes like this. Are you getting it now? So automatically, the first diagram here is your voltage, while the second one represents your what? Your current. Now, if you was explain what is actually taking place there, it means that your what? Your voltage and current are what? Are in phase. What does that mean? Voltage and current, they are in phase. They are almost at what? The same angle towards each other. They do not what? Lag anyone. You know, we said number one, we can relate your your resistor and your inductor. We can relate your inductor and capacitor. You can also now relate your what? Your resistance and your what? Capacitor. Your resistor and your what? Capacitor. So in this case now, we are only looking at resistor alone in your what? AC circuits. If you are looking at resistors alone in your resistor alone in your AC circuit, just link your resistor with your what?